Okay, so let me switch to the iPad so that I can use the pen. So here I go back to this. We would actually try to construct something, be it a constitutive law or something else, and then we need to just think about it like this is like a Lego exercise. You get given some building block, and I would like to try to build some to model that will reflect understanding of the world. Okay, so we will consider a modeling task. Okay, in a classical way, what we think about is the following. We have our observations, okay? We observe that the apple falling from the tree, for example, okay? So, but we may not yet have the data or actually have any descriptions to actually describe how the apple falling from the tree. And then we would actually perform the parametrizations of the observations. Actually, that would give us a sense of what is, for example, in the Euclidean space, would actually lead to generate some coordinate. And then we would describe the position vector, or maybe functions of x. And then we would actually parameterize the parameterized data, and the hypotheses are actually the constraint that lead to the model. So the model is admissible to both the data, so it should be compatible to the data and compatible to the hypothesis, or actually the principle that we think is actually the ground truth. Okay, so this is actually the classical way of modeling stuff in the Euclidean space. You can find it in just like the yield functions. We use the principal stress to find the yield functions. We make the underlying assumption that the yield function is only depends on the eigenvalues of the Cauchy stress. And actually we create a geometry by actually create functions that implicit functions that map the yielding into f equal to 0. That's the example. Okay. However, a lot of models are actually not best represented in the Euclidean geometry. The Euclidean geometry actually gives you some advantage in the sense that one of the important advantages is that it has a basis, and it has well-meaning orthogonality, and you can actually using this to actually build model. But there are a few situations that you know that the Euclidean space is actually not natural, or actually not necessarily the best way to model. So one thing to think about it is that equivalent space is actually a very special case where we build a model. A more general case, which you can see from Einstein, is that we need to consider not necessarily the writing the model that actually can be defined in a global coordinate system, but something that are actually something that are more complicated. In Einstein's generalized or general relativity, you can clearly see that because the space-time fabric are actually affected by the mass. So actually using Euclidean basis everywhere are actually really hard to contain the model or to express the model in a proper way. So instead, what Einstein discovered is that he need to use the pseudo-Riemannian manifold, which the tangential space, by the way, give us 3 different choices: time, light directions, and space, light directions, and nothing, and the null space. Okay, so we will talk about that in more details, but I just want to give you an example that if you actually have some geometrical effect that are actually not best described in a grid system, in a thing that can be using norm to actually describe the distance, then you need to think about some alternative machinery to actually describe the physical process. Another example, so this is actually more for the manifold example. Another example is on graph. So Euler, once upon a time, he went to vacations. So when mathematicians go to vacation, usually he do even more math, and this is actually what happened. He visited this city. I forgot where it is, to be honest. But he want to visit that bridge. So there are 7 bridges here. Okay. But he has a problem because he wants to visit all the bridge without repeating the path. Maybe he doesn't want to visit the same shop twice or for whatever reason. And he found that it's actually not really a good idea to use Euclidean space because you cannot cross other people's house to reach another thing. There's a geometry, there's a street that actually limit how his travel plan. Okay, so he come up with the graph theory. He just put the nodes on the bridge in this case, and then find out the connectivity. Does anyone know whether he successfully found a path where he can visit everywhere?
I think there's no path, and there's a really simple analytical formula where you compare like the number of edges and nodes, and you get like an even or an odd number.
Yeah. Yeah, I think if I remember correctly, you cannot, you have to repeat it somewhere. But there's a possible way to actually walk as little as possible, but there's no way you can actually not visit that. But anyway, so the beautiful theory of graph theory is actually born here. Basically, you can actually just consider those connectivity as the street that he can walk through, and then the nodes is actually the destinations, and then you can actually form a graph. Now, in these particular locations, in this particular case, the graph is actually a more natural way to represent the relationships and to create model. Okay, because quite frankly, you cannot actually visit it everywhere, and then the flatness of the Euclidean space doesn't give you any advantage. Okay, so those are two. Those are two alternatives that we're going to cover for the rest of the month. Past 1 week, that question, just let me know. And consider this. Well, this is actually not exactly true because the manifold, a manifold can be, is actually, could be locally Euclidean, but and not necessarily very smooth, but in general, you would actually use the manifold to describe something that are actually smooth, in particular for smooth manifold. And then you can use the graph to actually describe some discrete relationships. Okay, for example, social media, if you actually want to create a social network, is actually obviously much natural to represent it as a graph than represent it as a Euclidean space. You may embed the graph into Euclidean space, but the initial data will be on a graph. And in our work, we actually have to consider this quite a lot. In fact, you can. Okay, so this is just another two example modeling with the non-Euclidean options. When we formulate our finite element, we use the global coordinate system, but then the topology, the relationship of that, in this rapid case, you can actually either represent it as a graph, or you can actually represent the surface as a manifold. If you actually want to expressing the particular set of relationships with a discrete set of connections, then you would use the graph, because in this case, we are getting a set of point, which is actually lots of time. If you think about it in the global picture, when you try to model something, you often get data from a point. The point doesn't necessarily only contain the position informations. For example, you can have an earthquake network that actually represent the time history of the accelerations at the particular different stations, and then that station form a network. So you may have a time history in each node, but you don't necessarily have a Euclidean. The Euclidean locations doesn't necessarily be physically meaningful in predicting the earthquake. Okay, but you do have a point set. You can actually define the relationships by actually not considering globally what's going on, but consider among the edge, how do they connect to each other. If you're doing like that, then what you actually have from the point set is that you're going to form a graph. Okay, so the graph basically at the minimum is actually, you can describe it as an N triple. So a triple basically is a bundling between different sets. At the minimum, you would actually, the graph would have the vertex set, which is actually the number of nodes, and then the edge set that are connecting those nodes together, which will be something that we will talk about in details in this lecture. So we will talk about this. So this is the focus of this lecture. And then we have another point view, okay? Imagine that I'm modeling something that are actually changing very smooth among the point cloud, okay? Then the need to introducing an edge is actually not necessarily optimal. We are, for example, a surface, okay, or a curved surface, or if you want to recover something that have a smooth transient change in some parametric space. In this case, using a graph may not necessarily be the most optimal way. You want to define something in continuously, and then you would basically would try to do the manifold learning to see whether this point-wise observation can be converged into a manifold. In many cases, we will consider only Riemannian manifold. Okay, I'm not just trying to, I don't want to just throw a jargon here, but what actually means is that a Riemannian manifold is a specific type of manifold where the tangential space is actually inner products of a vector. So what actually it translates to human language is that if I actually have a space that we define it like this curve, okay, if I actually look at a local part of it, locally they are actually a Euclidean space, which is actually a space where you can actually define an inner product properly. Okay, so so the tangential space of the Riemannian manifold are actually locally Euclidean. And so what actually means is that if you have a Riemannian space and then you have 2 points that are very close to each other, you can approximate that distance in a norm, but actually not between here and here. Okay, that is actually too far away. We will introduce machinery. As you can see, with the point cloud, you actually don't know what is the right approach. So the choice of doing the graph learning or doing the manifold learning is actually really depends on what kind of perceptions you want to add to your model. Okay. And actually also sometimes whether it's convenient. So this comment is also coming from point cloud. Okay, so in the rest of the lecture, I will mainly limit the geometric learning into this workflow, and the workflow function as the following. I have some high dimensional point, and I don't know whether it's a graph or manifold, and in this case, this is actually could be a graph or a manifold, that can be both. And what actually we want to do is a classical machine learning task. We're going to convert it into Euclidean space in a lower dimensions. Okay, so this is actually, in the classical sense, we call it an upstream task. Upstream task is actually introduced in a sense like adjacency. We want to actually deal with a very high dimensional, very complicated data, but we want to represent it in a vector space. In a vector space, the advantage is that we can actually introduce regression much easier because of the existence of the coordinate system globally, okay? And you can actually also use the norm to give you the sense of distance, and hence the embedding, you can think about it as a problem where we actually want to reintroducing the data point, or we parameterizing all the data point onto a vector space, okay? So in the image classification process, this is actually essential. No one would actually use every pixel to build a regression model, but you are always embedding it into a vector space. And then that embedding is usually not a projections. So projection and mapping here have a very distinctive meaning. In projection, you just basically mean a linear mapping. But here, the comparisons of the data from the manifold or graph onto the vector space are usually nonlinear, okay? And in a special case where you can put those points onto a flat surface without changing the distance, you will get something called isometric mapping. Okay, we will talk about isometric mapping later, but not in this lecture. If you can introduce isometric mapping, you can actually reduce the data dimensions and compress the data without losing any information. So this is like magical. Okay, so I can give you an example. If I want half of a curve, and then I actually I have a scalar to represent some kind of level set here, I can bend it into a straight line and representing this nodes in the straight line. Now notice that in the curve, I actually, to describe the positions, I need the x, y, and then the level set functions, right? Okay, but if I can map it into a straight line, I only need the new x and then this. So I reduce one dimension without losing any information. If I can establishing the map that actually map the manifold onto the vector and then the vector back into the manifold. Okay, so in general, it's really hard to ensure that you can compress the data without losing information, but this is actually something that the machine learning could be used, and in a classical sense, the upstream task is often unsupervised learning. Unsupervised learning, or if you put a lot of constraint to it, you can also consider it as a semi-supervised, self-supervised, or something like some, etc., etc. Okay, so in this case, the next step is actually the downstream task. Okay, so downstream task is nothing special. If the upstream task is actually successful, that would make the downstream task much easier. Like the classification problem, okay, if I can converge the pixel informations into an encode-feature vector, encode-feature vector is actually on the vector space, then I would basically, using the vector as an input, I predict whether the picture is a dog or cat, okay? This would be a vector to, that would be a much smaller vector predictions to the other, to my prediction task. So usually this task is usually a supervised learning task. But there could be other exceptional case where you try to maybe do another unsupervised learning, or that is also possible to further sort out the data, or you consider way bigger generalizations of a much bigger data set, then you can do it hierarchically. But usually, in this course, we will limit to the classical machine learning deployment strategy. We have an upstream task and we have a downstream task, okay? So the downstream task is what we already talked about, that are dealing with the vector space predictions. And in a nutshell, what we're going to do in the rest of the month is actually roughly on how to obtain the upstream task correctly, okay? Does that strategy make sense? You have a difficult problem, you make it as simple as possible before you're solving the problem, then you solve the problem. Okay, that's the big idea. Okay, right? Okay, anyone still with me at this point? Or I already make it difficult? I will show some example and I will talk about the details. So why do we need to do that, okay? Why does the world need to be non-Euclidean except for writing new paper? Or to actually show that somehow we are smart or something like that, okay? Except the ego, what is actually important. Okay, so this is an example. I just took it from the internet. I just posed a problem here. And I think that if you go to EMI or US NCCM, you see that spiral thing all the time on the manifold learning on 1D. So 1D is a good example. Okay, so does anyone not know what is a principal component analysis? Principal component analysis is actually a very fancy name for singular value decomposition. So what does that do is that I will have this point cloud that's color shaped, okay? And then I would try to find a straight line that I actually minimize the error everywhere. So this straight line could be something like this, okay? So after that, what will happen is that I'm going to introduce projections. I'm going to project all the points. I really find the orientation that are the best. It's like the SO3, and I don't care what happened. I just collect all the points that are orthogonal to the extra dimensions, and then I will form a new data representation that are lower dimensions. So in the original spiral shape, the data is actually sitting in a 2D coordinate system, and then you have a color. So you have a point cloud that are sitting in R2, okay? And then I am actually going to using the singular principal component analysis and then to reduce the dimensions by exact 1 in this problem. Okay, so do you get the idea? Okay, I'm just trying to draw. I probably won't draw something like that because that doesn't look like the mean path to me, but I probably would actually have a line that are like that. Okay, so I compress the data by finding out what is the orientation of that straight line so that I can actually minimizing the distance of these projections everywhere, okay? So you can tell if I have a data that look like this, I can get the straight line, okay? Now, this is actually the linear embedding approach. You can tell that you lose some information, okay? And in this case, obviously, this is, you do actually lost quite a bit of information, but let's not talk about that. Another one is actually the manifold approach. The manifold approach, the major difference is actually this operation is completely linear. I draw a straight line, I actually project it onto a 1D curve, a 1D straight line, and then I reduce the dimensions. So here I'm going to do something very different. Imagine that this spiral line is actually a mechanical problem, like a rope. Okay, I'm just want to put it into a straight line. Okay, I create a deformation gradient. Oh, sorry, not deformation gradient. I create a deformation mapping, okay, for that spiral road and then make it a straight line. Okay, I can also reduce the dimension that way, okay, without any projections. And what I would have is actually this line. Okay, so both of them are reducing the dimensions. One in a linear manner, one in a nonlinear manner. Now I'm going to do the downstream task, okay? So this is actually an example of upstream task 1. And then upstream task 2. Okay, I make the problem easier by reducing the dimensions. And not only that, I only have a 1D case, and then I can actually using the distance to do regressions, okay? Now I'm going to make a new predictions. I give you one orange ball, and then you tell me on the left or right what is the new ball, okay? Now you look at it, the orange ball could be here. Okay, so, or maybe here, depends on what orange I look at. Okay, and then I look at the ball, okay? Then what we will have is that we may get a purple and yellow ball in this particular downstream task. But here, if I pick the, if I take the orange ball on the left and right, I'll get a more reddish yellow, more reddish orange, or actually a yellow ball, okay? So what caused the difference? Okay, what caused the difference? Okay, you see here, I'm actually adding assumption that all the data point cloud have structure, okay? And those structure are actually a smooth manifold. I don't know what is the manifold. I'm going to make the assumption that somehow that they are connected, and then in order to connecting them in the closest way, I would actually create a manifold. So this is actually the underlying manifold, and then I span it. Okay, so here, in the classical principal component analysis is that, okay, I actually do not necessarily understanding what is going on in the data, and then I simply try to assuming that the ground truth is actually a flat straight line, and then I'm trying to do my best to actually draw that straight line. Okay. So you can tell the difference and which one is correct. It really depends. Maybe the ground truth is really a straight line. Okay, you can make the wrong assumptions on creating the wrong manifold in general. But in this particular toy problem, you can see that learning the geometry or the underlying pattern could actually help you to comprehend the world in a more detailed way, in a more flexible way. And in this task, this is actually crucial because the order is actually not generating from the vector space. So you actually create a vector space here that are actually R1, right? Okay, but then that order actually make no sense, okay? You see what I mean? In fact, one of the machine learning hypotheses is called the manifold hypothesis. Have you guys heard about it before? Okay, so manifold hypothesis is the hypothesis that all the data that we actually obtain from the observations that are underlying low-dimensional manifold that are actually unmissable, that make all the points unmissable. Okay, notice that there's a hypothesis, and there's a few things to understand is that It's a low-dimensional manifold, not extremely high dimensions, okay? In this particular case, you can see that the underlying manifold, you just need one parameter. If you actually create a coordinate chart and the addness to actually contain it, you simply need only one coordinate system in the manifold. Locally, globally, in the ambient space, you need the 2D, okay? But actually, that can show one of the example. Now, can you do it in graph? You can also do it in graph. This is a very specific case of a graph that would be a walk. If you can generate the right perceptions, the understanding this is a walk, or in particular case, nodes that are actually just linked to each other, you can actually also make the prediction on the graph without any problem. In this particular case, yes?
So you aren't using like topological connectivity or like epsilon neighborhoods, you're just trying to somehow find the shortest walk by treating that as a graph?
You need to actually determine whether the edge is important because in most cases you're not giving the edge, you're just giving a point cloud, and you need to assume there's an edge. That is actually the difficulty. In some cases you do know, for example, Facebook, you know who is your friend, who's your wife, who's your husband, okay, so there are relationships that can be defined as an edge that are actually clearly known. In mechanics, a lot of time we do have an edge, like we actually have a physical test. We actually continue loading a material until it cracks, then we know there's a sequence on it, and actually it will form an edge. Sometimes it doesn't, then you won't have the edge to give you the guidance of how things are connected. I will talk about that. I want to say that not all the time, but in many cases, if you're giving a data, mathematically you can identify as a point cloud, and before putting a global coordinate system to it with very high dimensional, one thing that you want to think about is what is the right way to represent those data. Okay, a lot of time the embedding will be successful, and then you have a much easier job to make it happen. Okay, another example is that if you do micro CT on a microstructure, okay, that microstructure seems to be very high dimensional. I have 1,000 times 1,000 times 1,000, 1 billion of vertex. Okay, you won't build a regression task on that 1 billion input because a 1 billion Euclidean space with 1 billion dimension is crazy to make a prediction. So how do I even draw a hypersurface? How many points do I need? Okay, what you actually want is to reduce the dimensions of that structure as much as possible. In social science, that could also be a problem because if you reduce the dimension too much, you create stereotypes. So, okay, you see what I mean? So there's a controversial case where there's a study on looking at the people's look and determine whether he's a criminal. I think that creates a lot of controversial thing because you can't use the look to actually determine someone that whether is guilty or not. Okay. Maybe except feng shui, you can determine whether someone is rich or not. But in a scientific sense, probably it won't accept it. Feng shui probably won't accept it in the new IP conference. I think not in the near future. But here, I just want to point out an example. Okay, not to. So I want to say that in a nutshell, the geometric learning always have that two different favor, the discrete favor related to the graph, and then continuous favor, roughly speaking, continuous favor related to the manifold. So, okay, so it could take 2 years to touch each of the topic, but here we're going to condense it into 1 month, so that will be exciting. But not to disrespect other technology that I don't understand. So. Okay, so here, and then I'm actually also embedding my contact into a very small dimensional space. So yes?
If you're turning it into a graph, do the edges sometimes have weights attached to them? Like, can you attach like weights like as a function of distance to each edge of the graph?
You could. Actually, that's one interesting thing. You can actually put a lot of, you can actually, depends on how you treat the data, you can add a different type of edge to it. Some of the edge could be useful, some of them are not useful. I'm going to talk about that. Okay, there's a flexibility on that, and there's also a trick to actually make the graph data more rich and whether to make the embedding successful, which we'll talk about more in the next lecture. So here I just want to talk about some graph. Okay, so this is a vacation graph in the 1736. In civil engineering, we all solve a trust system. I think finding the faults in a trust system is the first thing that ChatGPT can actually do it in a 100% accuracy very soon. So I think that the structural analysis course may become a ChatGPT course pretty soon. But long story short, it's actually a graph. Actually, you simply the task of predicting the faults is actually predicting the node weight on the edge. That's it. Okay, and then this could be a very simple problem if it's linear. If it's nonlinear, it's still doable. Predictions on social networks, so that could be a more lucrative problem than solid. You can using it to predict who will vote in the next elections. You can actually using it to predict who is going to buy certain item, and you can build causality on the graph. If someone in the nodes is looking for table and bed, someone is probably moving. And then if he move, he probably move if it's all his children, family, blah, blah, and then they will be looking on stuff. So if they imagine that Facebook can locate this family, they would actually keep showing stuff that are actually related to that. Not always accurate. I would say that when I start the sabbatical at Stanford, I keep getting those YouTube about buying house, but they overestimate my fortune. So I don't really have the money to buy a house, but they kind of detect my moving, but not exactly the. So sometimes this could happen. Fake news detections. Fake news has a very different characteristic of publications news than a real news. One interesting characteristic is that they tend to come from a fewer source and then propagate, compared to say a Turkey earthquake, where multiple news outlets will actually obtain that news and then propagate. So you can actually use the graph feature to actually detecting that. Another thing that are actually really game-changing is the chemistry. You can actually see that molecule are actually form a graph because the individual atoms are actually naturally form a nodes and then they're connected to each other. And using a Euclidean space won't give you any advantage, but using the nodes, the edge to represent the bond, and then the atom to represent the nodes, give you a very expressive, very economic way to represent a molecule in a mathematical way. Okay, so what I'm going to do here is the following. I'm going to introduce what is a graph with all the details. I know many of you have taken a much superior graph neural network course, 224W, and I'm also taking that course, but so here I'm going to do something different. I'm going to tell the details of the graph one by one, and then just talk about the thing related to the mechanics. Okay, so just remember that basic details. As I said before, a graph is actually basically just two sets combined to each other. You need some nodes, and then nodes can be very abstract entity. It could be a voxels, or hopefully not. But it could also be a human being, or it could be a crystal, or it could be a particle, okay? And you need to represent their relationship in a nodes, in an edge. Okay, so if you're connecting it in this way, for example, you get a triangle, okay? So this edge, for example, A, B, C is the edge, and 1, 2, 3 is actually the nodes. I would have the vertex set that I actually call 1, 2, and 3. Or maybe and then I would have the edge set that I actually A, B, and C. That's it. Okay. You may notice one thing that are actually already different. In the Euclidean space, I can easily obtain the gradient and divergence, but here, I don't know what does the calculus actually mean physically. Okay, so there's some limitations. A lot of time you build the Gaussian equation using the derivative, right? Okay, I have that ODE. Okay, you take a derivative over time. So here you can say that, imagine this is actually 3 person and how much money they earn. And then they have some relationship, maybe they're sibling or we can something. You cannot actually take a gradient of the sibling and then determine what is the second brother earned, how much money they earn. Okay, but there are actually a way to actually introduce a vector space that that actually are related to the use of the embedding. Okay, so the most basic form ingredient is that you need to have a vector and they need to somehow connect. If you only have the point set, then you will only have the vectors. And I cannot imagine how you can only have the edge set. So I won't actually talk about that. Okay, and then there's another thing, which is actually, let me get into the more details. These are indirect graph. So graph could actually have directions. So what it means is that I actually have the graphs that are actually vertex and actually Y. Okay, indirect graph is actually a specific type of the graph where we don't care about whether the connection have a direction pointing to A to B. Okay, so a good example is that if you have two particles that are touching with each other, then one way to represent this is actually represented as an undirected graph, okay, in this particular case. And the important thing is that in an indirect graph, you don't represent a cause, effect, or actual hierarchical relationships. Okay, so edge has no directions, meaning that going to the left and going to the right mean exactly the same thing. For example, granular ensemble could be a good way to modeling it. In petroleum engineering, we often use the pole network model. The pole network model is also undirected. However, family tree is not good to model it in an indirect graph for obvious reasons. So the grandparents born the parents born the children. There's a directions, and also another thing that are actually a very common example is causality. Causal graph are actually always direct graph, or it could be a mixture of direct graph and correlation that doesn't have directions. Okay, so this is actually the graph. Just bear with me, I'm actually going to introduce this. Okay, so and then there's another concept. In general, between two nodes, a graph can only have exactly one edge. Okay, so you could actually have the edge that have multiple weight, but there is only one edge. If you are actually allow multiple edge to actually exist between the two edges, then it doesn't form a graph. It forms a generalized concept of a graph called multi-graph. Okay, a multi-graph is actually useful to actually represent a family of concepts. For example, I want to model the material between the strain and to stress, but I can actually choose whether I want to use a Neo-Hookean to actually model the stress, or I can use linear elasticity. Okay, you can actually embed those choice into a multi-graph, but it would be harder to represent if you actually want to represent it in a graph. Okay, so that would be an economical way to represent choice that you haven't, because in this case, the multi-graph gives you flexibility. Let's say I have 10 different ways to model something, and then this stress could maybe lead to a finite element solutions, or using finite, or maybe I can get the displacement from that, from the finite element, from the finite volume, blah, blah. So you can represent a choice conveniently, and for example, I can say that I make this modeling choice. Okay, so the multi-graph is actually useful in the sense that it can represent a game broad, or actually all the possibility of doing something. And then the graph would be a subgraph of the multi-graph that become a really real graph, not analyzed multi-graph. Okay, so here we won't do any of the difficult thing. Our goal would be only focus on the simple graph. What is the meaning of the simple graph is that the graph that doesn't have the multiple edge, like what we talk about in the multi-graph, and doesn't have loop. Loop is something that map to itself. Okay, so I'm just taking out that possibility. Mapping is sometimes with relationship between the node itself could also be useful, but we won't actually consider it here. And then I just want to introduce more terminology that would be useful later on explaining what is a graph autoencoder. Two nodes can be connected, and if they're connected, obviously they're called neighbors, right? Okay, just the English meaning of neighbor, or you can say that they're adjacent to each other. Okay, you can actually think about it. There's a very convenient way to represent the nodes connectivity is to represent it as a matrix. For example, I can name this as 1, 2, 3, 4, and 5, okay? And then I can build a 5 by 5 matrix, and I'm just saying that, okay, if 1, 2 are actually connect in the 1, 2 direction of the matrix, so let me put all the 0 here, just to give me a sense of directions. If this is actually connect, I just put the 1 here, and then I can actually, if 1, 3 are actually connected, I would also put a 1 here, but 1, 5 are not connected, 1, 4 are not connected directly, then I just put the 0, etc., etc. So I can represent this, the global connectivity with a matrix, and that matrix is called adjacency matrix. Okay, so far so good. Okay, so if a pro network, adjacency matrix is actually quite useful because it tells you how things are connected. Okay. Now, and this is actually the way graph that we want to talk about. In general, if I actually describe the data in terms of the way, in terms of just the, if I describe the graph as just the vertex set and then the edge set, I would actually get an understanding about whether they connect. Basically, I get an understanding of the topology, but I won't necessarily make the most of the applied applications. So usually what we need to do is to add the way. Okay, way is actually not physically a way, unlike related to mass. It's actually a way to contain extra informations. Okay, so a way itself is a mapping. Okay, and there are two types of mapping. If we actually have a vertex set, it could be usually mapped into an n-dimensional Euclidean space, or for a given nodes. So, for example, if I want to represent a network about Stanford student GPA, okay, so the GPA of the individual, so the individual student would be modeled as a nodes, and the GPA would be actually modeled as a node way, okay? And then you can actually study whether they study together in a group, and then you can add the edge there, for example, and you make the predictions next semester what is their grade, okay? And whether they're cheating also, sorry, but okay. So this is one way to represent this would lead to a node way graph. There's also another option is to actually put the way on the edge. Okay, and then n could be anything that can describe the behavior. So okay, or actually could be some feature. So the way can also be put into the put into the edge. The node way and the edge way are actually a flexible concept for you to put different type of information there. You need to introduce your physical understanding to put the right way there. For example, in a pole network, okay, I have pole center 1 and I have pole number 2, and then they're connected in a pole network. So what should be on the edge way? Okay, so usually you put you can put the distance there, but you can also put the radius of the tube that you put in there. So that would be a right way to actually describe the full network, to describe the material. And for the node way, you basically put the radius of that circular or spherical nodes to it, okay? And I want to say that the more way you put in there, the more descriptive your material it is. The way and then are simply numerical number that for you to describing the individual nodes and individual connections, okay? So maybe I can give another example. That doesn't necessarily to be map it into a real number. For example, in a social network, whether you guys are friend or close friend or relative or family, you can also map the edge into a set, and so does the edge. So does the nodes, okay, or actually the vertex. Okay, so far, do you guys understand the basic concept? Okay, so it's actually the playground for you to actually choose how to describe something. The more edge, in general, more feature you put into the way, you increase the dimension, but are more descriptive, so there's a trade-off. Okay, so, and also another thing is that usually you don't put the way that are actually are not provide you new informations, okay? So for example, if I actually describe a vector, if I have a vector that are 1, 0, and another one is 0, 1, you don't add the coefficient of 1, 1 onto it. Okay, so that would actually make the learning much harder because of the vector only span into R2 and you don't need 3 bases. Okay, so usually you put new information onto the edge, not information that can be determined from the rest of the set of the way. Okay, you understand what I'm saying? For example, you will put if you put the radius into the way, you don't put the diameter. Okay, so otherwise your trick would be very difficult. Okay, and then I think that oh, by the way, another thing that are very important to know is that let's say you start with a way that you start with a graph that actually have no way. Okay, you can also enriching the descriptions of the graph by saying putting the number of edge on this node into the way to actually form an artificial way to actually enrich your data representation. The reason you want to enriching that, I will actually talk about it in the later slide. Okay, adjacency matrix, I think is actually pretty easy to understand. Do you guys get the concept of how to write an adjacency matrix? Okay, I'm just go for that. Okay, another thing, just bear with me, we are almost into the machine learning. It's actually the sense of degree. Okay, degree basically tell you how many edge you actually have. So we call it an incident between the edge and then the edge and the nodes. And then the nodes that actually have the degree of a node or the vertex actually depends on the number of incident it has. So in this case, you have 1, 2, 3, 4. So that would the degree would be 4 in this particular nodes. Okay, so here you will actually have degree of 2. Now you can think about it. If you're a hacker, you want to attack a server. Okay, are you going to go for the degree that are very high or very low? Okay, you're going to attack the one that have very high degree because once I actually control that nodes, I probably can propagate it almost everywhere. Okay, so this gives you a sense about how, in a sense, how connected these nodes is. You can also see it from academia. There are papers that actually connect to all the other paper, and there are papers that are actually in an interesting way become a walk, or there are papers that are like a tree. You can. And you can see what happened there, maybe in a way. Okay, so one last questions that are very important is that I have all those graphs. Remember what is my task? I have all those graphs. I want to put it into the vector space. Okay, what does the embedding mean? Is that I actually need to put the graph that are very different. That if I'm embedding into a vector space, they need to be very far away. And then the graph that are very close to each other, they need to be very close to each other. Okay. So now there's a two graph here. So let me ask you the question, are they identical? They don't look identical, right? But the way I asked you already indicated, right? Okay, so what's going on here? Okay, so there's a very important concept, is that how the graph look like doesn't indicate that whether they are actually identical or actually related to each other. What actually you want to see is whether they can create a bijective map. Okay, so what is a bijective map? Let's take a look here. Okay, and I already give you the color because I actually cannot see that they are identical by my own eyes. My brain is not big enough, but after putting the color, and by the way, it's just download from Wikipedia, so I do know the answer. Okay, let's look at node 1. And then node A and see what happened, okay? So, and then you can kind of extrapolate to get all the answer. Okay, node 1, what is the neighbor does it have? It has node 2, and then it has node 4, and it has a node 5 as the closest neighborhood, right? Okay, now if I actually look at it in detail, in the neighborhood of 2, I will actually have 1, and I have 3, right? So I have the nodes itself, 1 here, 1 here, okay? But 2 have a neighborhood of 1 and 3, right? Do you agree? Okay, and then 4 would actually have the neighbor of 1 and also 3, right? Okay, so I'm correct. 1, 4, and also 8, sorry. And 2 would have this and also 6. Okay, and then 5 would actually have the neighbor of x, 6, and 1, right? Okay, does that look okay? Now I'm looking at note 1. I'm looking at A here. Okay, so A would actually have a neighbor of B and I and also G, right? Okay, is it correct? Oh yeah, sorry, H. Okay, so wait a minute. So did I pick the right notes? Oh yeah, that's no B. Okay. So let me put the B here. Okay, and what is the neighbor of I? The neighbor of I would be C, D, and also A. And the neighbor of G would be actually A, B, and C. And the neighbor of B would be J, A, and sorry, I don't have B, right? That one is actually H. The neighbor of H would be A, D, and A, D, and B. Okay, so I kind of want to give up on the rest of the notes, but I can tell you the answer is right. If you check every notes, you would find out that it leads to the exact same compilation graph, meaning that if I rearranging them topological Y or the connectivity between the two things are actually identical. Okay, so what it actually means is the following. The important concept is the following. I may not get the same adjacency matrix, but the adjacency matrix of this graph, let's say A1, and the adjacency an adjacency matrix of the graph number 2 are actually related just to permutation tensor. So permutation tensor basically is a tensor that only have 1 and 0 in the following sense that it's just rearranging the label of the nodes. Okay, does that make sense? For example, if I have 2 nodes and this is called 1 and 2, and want to swap it to 2 and 1, I just assign the adjacency matrix of 0, 1 and 1, 0. I can swap the order. Okay, sorry. Make me a little bit nervous on dealing with the graph. So, okay. Now, why does the degree and the adjacency are actually important is that they're related to the graph Laplacian. Let me actually explain it why. Okay, so in the simplest sense, the graph Laplacian is basically just the degree. Is actually just the degree matrix minus the adjacency matrix. If you put the weight there, you can also on the adjacency matrix to give you a sense of distance. The graph Laplacian would actually related to d minus w. And you can also create a normalized versions of the symmetric normalized Laplacian matrix, which can also be described the relationship among the different nodes. Okay, so now this is very abstract, but what does the Laplacian mean? Okay, so so how many of you know what is the Laplacian in the Euclidean space? Okay, it actually needs to two things. So the triangle, by the way, is not the delta. Okay, so if you write triangle P equal to 0, what actually I'm telling you is that the divergence of the gradient of P is actually equal to 0. Okay, what is the divergence and gradient of P? Okay, so let's say I have a scalar field that actually look like this. Okay, So what is the Laplacian? So what is the gradient? The gradient is actually the field that are actually related to the, is actually the change along with two Euclidean space coordinate. I'm actually going to, this is basically a vector. So if P is a scalar, P is gradient, P is become a vector. That tell you if I actually going to the change in the one directions, and then I'm going to change, and then I measure the change into the two directions. E1 is here, E2 is here. Sorry, and then I would actually create a vector space. I will create a vector that I actually point to the locations of where the scalar function is actually changed. Okay, what does the divergence mean? Is that you just sum up. You basically have the chase of that. You basically are actually adding those terms together to get a sense of how does the change look like. Okay, so if I actually, you probably know what does that mean. Is that I will probably just get this square plus y equal to 0, right? Okay, if you actually remember it from the undergraduate some mechanics class or other PDE class. Okay, so this is actually the Euclidean space graph Laplacian. So what is actually the Laplacian in the graph that doesn't have the sense of the gradient? Okay, so imagine that I have a system and then I want to define some gradient. So gradient may not make sense, but I can define the difference between A and B and D and A and C. Okay, now I actually doesn't guarantee to have a neighborhood because it's not a grid system, but I can actually represent the relationship in a graph, and then I have those edge. And if I actually want to describe this, okay, the feature of A minus B, I can put the incident here in 1 and minus 1 to indicate that I'm actually adding, I'm having this minus this as an operator, right? Do you get what I'm saying? So this edge, let me clean this up. This operation is mathematically represented here, okay? The same for B and C and B and C, and then A and C and B and D, okay? So if I do this, then I form this incident matrix. Okay, so everyone got it? Transpose of, so a gradient term is basically the incident matrix times the node feature. Okay, in this node feature, maybe I call it X. Okay, this will give you the gradient of X, and X is actually equals to the node feature in A, in B, and C, and D. Okay. Now, what is a graph Laplacian? If you study finite element elasticity, do you remember what is a B matrix? So B matrix is actually quite interesting. If you apply the B matrix, you get a strength, right? Okay. So how do you get the stress for linear elasticity? You apply the BT, CBU. Okay, assume it's linear elasticity, and then you actually, what is this actually represent? Okay, so actually is related to width form, but here, what we actually say a divergence is basically the, so now the Laplacian term is basically the transpose of this, and then from that, if I actually compute the transpose of the K and then apply it to the gradient term, I would actually get this. And something that is interesting is the following. And then I will not proving that, but you can try that at home. If you actually compute the divergence and the gradient operator together with that the transpose of the incident matrix and the incident matrix itself, you get the graph Laplacian. Okay, this is actually equals to the degree matrix minus the adjacency matrix. Okay, so in a rough sense, the graph Laplacian gives you the sense of how smooth these things are even without the Euclidean matrix. So I would say that if the whole class have a GPA of 4.0, then what happened to the graph Laplacian? Okay, so it will be very different than the whole graph that actually have the change that are actually very doesn't have that much correlation. So the graph Laplacian, it could be directly put into the graph convolutional neural network, or you can actually, in a sense, if you actually use the PYG, it may already compute for you, so you may not even aware of that. But underlying it, the convolutional neural network, the input is usually the graph Laplacian or the normalized graph Laplacian. That actually give you a sense of how to actually do the aggregations of the informations. Okay. So here I just want to give some example, and also for the rest of the lecture, I want to give you some idea on what could be a project that are actually on a graph. I would say the following. In the final project, you can do the first part of the class, maybe writing an elasticity model. But I think that I would like to see that you either apply the metaphor or actually the graph learning for your final project. Doesn't necessary to actually, you don't have to prove the Poincare theory or something really advanced, but just do some very superficial application of the graph and just compare with and without the graph whether this would be doable. Okay, so and I apologize that I self-promote myself a little bit, but I think that I know the paper I write myself, so, and then I did not study hard enough to study other people's work, so that is another disadvantage. So one possibility is that if you have a micro-CD image, you can think about how to represent the micro-CD image as a graph. Now, there's a jump here, okay? Your voxel image is actually inherently Euclidean, okay? Because you are actually putting it into a grid. A grid have a fixed side neighbor, and then they are actually all, and then they're connected in the sense that you can represent it as a graph. But if you try to do the graph convolutional neural network, you will find that you get no benefit because there's no special topology that actually give you the benefit of using a graph neural network. However, there are ways that are actually very important in the sense that the physical graph are usually in engineering application, they are actually not the computational graph. Okay, what does that mean is that, let's say I have this imaginary voxel space. Okay, I actually don't have to consider individual voxel connect to each other because that gives me no advantage on representing that topology. What we actually need is actually you can do a compression on the data by finding what is the medial axis. In this case, I'm just solving a sign distance functions and then link the vertex and then link the local maximum together, and then I will get that skeleton. Okay, you just need the sign distance transfer, or actually in MATLAB it's called skeletonizations. And once you skeletonize, what do you see? You can see that you see a metaphor, or you can say that you see a graph. Depends on whether you want to continue representing it, or you want to represent it discretely. So in this particular case, what you can do is that you can add those nodes only in the junction point. There's option 1. Okay, and then you can actually using the way to represent the size of the radius. And then you can using the edge to describe how they're connected. And you can use the edge range to describe the geometry of how does the edge control. And the geometry doesn't necessarily to be voxelized. You can actually parameterizing it as a cylindrical object, or you can allow these two have different radius. So you can create some kind of low-dimensional representations of the using the advantage of the graph. Okay, so that would be actually much smaller. You may lose some information, but you can, if your geometry is not so complicated, you can actually represent a lot of details with a much economical way. That's one option that you can think about it and think about how to do the embedding. I think what Ming did is that he gives you some heat conduction problem with different boundary, a collections of problem, and then embedding into the space. So here you can think about what is the right way to embedding it. If you don't do anything, that's possible that you can just use the brute force convolutional neural network on the voxel space. Okay, you can actually take the average. You can doing it. That would be fine, but it will be interesting to compare. One thing that maybe we want to talk about it later is that, let's say this is a permeability, and then obviously that permeability is not going to be isotropic. It doesn't look like isotropic to me. So I will have K11, K12, K21, and K22 here. Now, if I rotate that image by 90 degrees, okay, so what you actually want is the K22, K11, K12, K21. Okay, so the off diagonal, I'm assuming that is positively definite and symmetric. Now, do you get that in the convolutional neural network? Okay, I can tell you the answer is no. Okay, without actually enforcing the specific rules, you would actually get the wrong perceptions. Okay, you may get a very accurate K11, K21 projections, but then when you rotate the image by 90 degrees, you would not get the tensor that are supposed to be the rotations of the original coordinate system. Okay, that we were actually addressing it later. In order to go over that, we need to enforce the equivariance there, and there are equivariance convolutional neural network or an equivariance graph neural network that can actually doing that. It's available in both graph and in a metaphor form. Okay, so this is one project idea. Another project idea is actually on the microstructure that I have assembled. So this is a polycrystal. Okay, so a polycrystal is actually a group of single crystals that are actually connect to each other. The crystal is inherently itself anisotropic, but you can actually thinking about this naturally as a network. Okay, that are for different crystal of different shape connect to each other. Now, the interesting thing is that if you actually describe it in the nodes, in this period example, it's actually quite important that you actually have the node weight and the edge weight, because the edge weight does matter a lot. But in this case, if you describe the particle in a very complete way, the edge weight would still be important, but you can actually make a pretty good approximations. Okay, so you can actually using the node weight you can actually using the node weight to describe how does the particle shape look like. This could be done in another way. You can in any arbitrary way that require your creativity. What would be the choice for you to describe the particle? Okay, in 2D you can actually have this particle. Okay, or maybe a polygon or this. So how do you distinguish all these particle shape? Would be the way that you want to introduce. So like what I said, you can actually do the unsupervised learning in both levels. You can do it by first do unsupervised learning on the individual particle shape first, and then actually using it as a way into the graph, and then learn the different graph. You understand what I'm saying? Do you get the idea? Maybe I describe it again. Okay, I have two collections of stuff. One is the collection of polycrystal. Okay, do you get it? I have many polycrystal, many of these assembled. Okay, but I can view it in a hierarchical way. Individual particle, I also have thousands of different particles. Okay, so how do I actually embed it? How do I actually find a good way to represent it? So that form a hierarchical system, because for the individual particle, I can embedding it into the vector space to describe it. One example is a Fourier descriptor. I will using sine, cosine functions, and then put a radial here, and then actually try to represent the shape. And then I can embedding it, and then that will form the way of the nodes that are already in the embedding space to describe the shape. So that will be the shape descriptor. And then I can actually create the And then you can create a sample of different polycrystal. You can actually embedding that polycrystal also into a vector space. And if you can do that, then that vector will give you the descriptor of the whole different polycrystal shape. Okay, do you get the idea? So if you publish that idea, remember to put me in the offer list. So just a friendly reminder. So anyway, so this is another possible project, okay? Another project is actually, another idea could be done in this way. You don't have to do any of this. I'm just throwing in some possible way, okay? Another way is that I don't consider the multiple ensemble. Now the thing about this is actually powerful in the sense that if all the embedding are successful, I would not create a circuit for one microstructure. I would create a circuit for the entire family of microstructure, okay? Okay, you see what I mean? That means that in the new predictions, if I have the micro CT of a new polycrystal, I will immediately get a personalized, sorry, not personalized, customized energy functional that are only designed for this particular microstructure without running any new thing to create a new model. There's also another possibility is that, let's say I just want to create a circuit for one model, but here I'm considering the revolutions. Okay, so for the revolutions, this is a DEM. I actually try to share it, and I form this a false chain. Okay, you can see that where the contact is actually getting large. So it will evolve the edge as the contact become connect and not connect, and when they connect, how much normal force it will have, it will create a history. So another possibility is that how do I embedding one particular graph that evolve in time, okay? So that would be another possibility on the convolution neural network that involve the graph and the time. So for those of you taking the graph neural network course, you probably know the neural network dynamic graph neural network. For LAN, for example, you can try to do this. This is possible using Ronan. Just don't put too many nodes there. If you put 1 million nodes, I think that it probably won't work. Okay, so now there's another possibility. This is not my work, but I think this is also something interesting. Imagine that you have a sample and then you deform it. Okay, so you don't necessarily need to use the nodes and the edge to store a spatial relationship. Okay, it could be related to deformation gradient itself. Okay, so for example, I have an undeformed shape, and I actually apply the deformations to the original deformation. I get another shape, and I deform it. Okay, and then I will have another shape. Okay, so you can actually using the edge ray to represent that mapping from one configuration to the other configurations, and then you can actually say that I can also directly map it here. Okay, so you can also form a graph by considering different deformations and store the work. The interesting thing is the following. That gives you a new perspective on how the model to stress. So if I have a new mapping, how do I actually predict what does the nodes looks like? Okay, so it become a node embedding problem. Node prediction problem. That could also be done in this way. Okay, so you can kind of see the graph give you different. So the foundations here is the following. I don't mean that I'm always correct, but based on my experience, what I see is the following. The important thing to use the graph is using the graph as a mathematical tool to actually let you see the work in the lens of graph, okay? You understand what I'm saying? And sometimes you don't actually want to see it in terms of graph. Like in a grid system, you get no benefit, okay? But for social network, for example, you get the benefit. For polycrystal, you can clearly see that how these things connect. You can see the benefit for porous media. You can see a lot of benefit, for example, because, you know why? Because if you actually want to predict the probability, for example, on a sandstone that have a porosity of 20%, all the voxels that in the solid phase are actually give you no informations. Okay, the underlying pattern is actually very low dimensions, but how many dimensions can you reduce is actually very important. So what is a smart way to reducing it? Okay, so you see what I mean? So I will give you the following. If you compute probability and you're using the color image to actually do the convolutional neural network, you would not actually get a good predictions because the solid phase have different color. but those color doesn't actually affect the permeability. Okay, you see what I mean? So when you use the convolutional layer, you will get a different informations. Okay, so the important thing is the following. One approach to think about the machine learning problem is to think about how do you compress the data before you actually even doing the downstream task. Okay, so this is one thing that are actually important. Another thing that that could also be a good idea is related to the knowledge graph. The knowledge graph here, I'm not going to mixing different graph together just to make it easier. You can think about how do I actually create a direct graph. Okay, so there's a technique for a knowledge graph embedding, but when you create a model, you also need to explain the mechanism. Okay, how does the CAM-K model, okay, I'm saying that for different porosity, I get a different compactions and dilatancy. Or actually for permeability, porosity relationship, I'm saying that if I open up the walls, I get more permeability. There's a causality here in the permeability. In hydrology, the very famous relationship is permeability linking it to the permeability. Porosity linking it to the permeability. So there's a causal relationship to it. Given a change in the porosity, I would actually change the permeability. Okay, but there's a difficulty here in the following sense. How many of you have tried to curve fit the porosity permeability? What you get is actually a very, very large group, kind of like the manifold problem. And then I'm going to draw this. By the way, it's already in log scale. Okay, this is actually log K. I'm saying that if I predict it within the same order, I did a pretty good job. And this is related to porosity. Okay, so why is that? Okay, why would we always get that? Have you ever wondered? So, student from energy resource engineering, any answer for that? I'm looking at you. No, I'm just kidding. No pressure on that, okay? So there are multiple possible explanations. It could be the uncertainty, but there's another way to think about it. What if I simply missing some dimensions? Okay, you see what I mean? So what if there's a new dimension I actually don't know it exists? Okay, and then if I put it into the new dimension, I actually have a surface that are actually pretty smooth. Okay, do you understand what I'm saying? Okay, so the causality, another thing that would be interesting is that can you determine the causality? Can you check the causality, which we will talk about? Can you detect the dimension that are missing? Okay, so imagine there's a tomato here, and then there's a wall, and then I do this, and then the tomato is going to collapse into some juice that are everywhere, right? Okay, this is exactly what happened. I collapse one dimensions. The whole thing can be deterministic, but because I actually don't know all the dimensions to write a model, I collapse one of them. Okay, for the solid mechanics, you can think about it like a thermal elasticity problem. If you have a steel and then you're actually loading it in adiabatic conditions and you forget to measure the temperature, you would also get something like this. Okay, but if you look at it in the temperature dimension, you actually have a unique response. The reason that you don't get a response could be the lacking of the dimensions. Okay, but in general, you don't know the dimensions and you don't necessarily have a physical descriptor for that dimension. So one way to think about it is that the income feature vector that you do the embedding give you the dimensions. Okay, you understand the idea? Okay, so I can actually describe the porous media in terms of porosity, in terms of conductivity, in terms of degree, in terms of graph connectivity. I create a descriptor. But another way is that I would directly using the Latin space of the micro-CT to create the geometry or the dimensions in the embedded vector space. Then I would actually cover the whole thing, hopefully, right? So that's the underneath idea. I actually talked about that before. You can think about the PDE solver also as a direct graph. Obviously, you may actually, it's actually work function kind of like a neural network. You can think about it. The constraint is here, and then you predict a U, and then once you predict the U, you propagate that information, get the constraint, and then you update this whole thing back. Okay. You can think about it, if you build a solver, you are really building a direct graph. And then what is the right way to think about the model is not necessarily thinking about it as some kind of balanced law that are actually connect to each other, but thinking about it as a graph about how what is a causality. Okay, you may not know that, but when you write a paper, in particular like a finite element paper, you always create a graph. Okay, you see what I mean? In particular, you always create a direct graph. So how do you actually check whether this direct graph is actually meaningful? That could be also be another thing that could be very interesting. Another thing that doesn't require that much mechanics knowledge, but could be done, and this is actually from Professor Ortiz's group, is on rematching. If you actually really enjoy doing rematchings, this is your golden opportunity that you can actually doing that. Okay, imagine I have a crack. I just want to do it in 2D just to make my life a little bit easier. Okay, I can actually thinking about a crack as a modification of the graph that I simply add a new nodes. Okay, and then I create a new edge. Okay, and then the advantage of this is that these things are actually universal in both 2D and 3D in the sense that you can have a nodes, and then the nodes give you the line give you the surface, in this case a triangle. The triangle form the volume, and then the volume together form a map. So collections of tetrahedral elements form the entire 5-element mesh, and the collections of surface, in particular 4 surface, form a tetrahedral, and each tetrahedral have 1, 2, 3, 4, 5, 6 edge, and then each edge have 2 ends. Okay, so if you think about it like that, you can create an arbitrary factor by actually creating a new tree. Okay, so you can actually think about it as a project. If I have a mesh that I already meshed and I want to propagate a crack that maybe look like this, some crazy nodes, what is the corresponding tree? That could also be an interesting final project. Okay, that actually could be quite helpful because it helps you manage the memory and design what is the right way to create the embedded strong discontinuity. Okay. Another thing is that, like what I say, you can also do multi-graph. So if I actually don't know how to write a model, or actually I have a material library, I can put all the possible way to model the same thing into a multi-edge, and then I simply pick the particular nodes. So this is just a very simple test in the sense that I actually build a master constituted law that contain all the different possible way with a 3 invariance specificity. More accurately, my student did that because I think there are thousands of edge, and each edge require return mapping algorithm as some modifications. So and I think that student is in ExxonMobil right now, earning way more money. So I don't owe him anything, maybe in some sense. I'm sorry, I should stop recording that part. But anyway, but the true story is that this is actually also another thing to test is the following. If you actually write a constitutive law in a master scouting key level, you can put all the possibility into the edge, and your verification problem involves picking what edge set to be activated, and you can actually have one master constitutive model to trigger all the different constitutive response. You don't have to write one for steel, one for rock, and then when I actually have something interesting, you don't know what to do, or maybe you have something that composite of the rock and steel. I'm just making an example. You may come up with some new combinations. It may not work well, but the data in that case, the inverse problem is not only finding the material parameter, but also identify the edge among the available edge. So that could be a new design on the material library that are actually easier to use in the sense that the data set itself will trigger a particular way of a constitutive law. Okay, does that make sense conceptually? This could be one of your final project, or maybe I can assign the final project so each of you did one. You can try. I mean, this one I actually did not make it very big. Just on a phi invariant thing with some arbitrary shape, and then I just. And then the last one is not a final project. It's just to check that in the old day, if we right now the the path searching algorithm is actually not obtained by spanning the minimum tree, but in the old day, you can actually solve something called a minimum tree problem to identify the shortest path of something. Okay, the shortest path in some case could be meaningful for a particular problem. Like if you're actually driving or you're taking a Uber, the shortest path is actually what determining the cost. And here you can apply some interesting idea here. In this particular case, I'm just using the distance of the path from point 1 to point 2 to define the distance. But you can also use time, okay? In fact, you can argue that time could be a good indicator for a price model because the driver are actually using that want to earn money as fast as possible, right? Or you can actually put time plus the gas in some way constraint to create the edge, because in order to earn money, I need to spend as little time to actually travel as far as possible using the minimum amount of gas. Okay, so that could be. But you actually also have some other problem in the Uber because some people are driving Tesla, some people are driving a truck. So how do you normalizing this to actually calculate the profits? Okay, so you actually need to deal with the different work for different person. I actually need to customize to create a different graph. Okay, so a driver that are driving a van would actually need a different way than people that are driving a motorcycle, the person that driving a motorcycle, if there's a Uber for motorcycle. Okay, so this could be one thing to think about it. I just want to give a more concrete example here. I think I still have some time, if I think. So let me continue this. In this particular time, like what I said, we can, in this particular polycrystal example, you can actually, the key idea is the following. My goal in this first task is to create a generalized model. Okay, in most of the handcraft model, they are not handcrafting a constitutive law for a particular microcity image. They're actually model sand, steel, aluminum, but not a particular aluminum microstructure. Okay, so but when you're actually using it in a multi-scale setting, you're often corresponding your data set with a microstructure RVE, and you keep running the simulations. That would make the model very specialized and not able to use for other situations, okay? Because each microstructure is unique. And then if you actually have a different microstructure, the permeability could be completely different. The Young's modulus could be completely different. So you need to actually create additional control on it. And one way is to directly put the graph inside. But as I said before, if you put the graph inside and then the graph only have 5 nodes, I think that's fine. But if you are actually consider a polycrystal that have median of a gram, maybe medium is exaggeration because I think medium will make it really hard to embedding it anyway. But if you, let's say a couple thousand gram, then what you actually want to do is to write an energy functional that actually given some kind of deformation measure, maybe F, maybe E, and then and the graph, and then come up with a new predictions that if I take the gradient of F, I would actually getting the P, the first critical stress. Or in small deformations, I would actually write an energy functional that given the strength and then the graph, that could be the energy, and I change the microstructure, I will get a different energy functional. Okay, so that's the key idea. But if I take the partial derivative of it, fixing the microstructure, I will get a particular stress for that particular energy functional, for that particular microstructure. Is that clear? You can do it for permeability as well. Okay, this is the same thing. You can actually compute this. You can actually form, in the linear case, this is a quadratic functions. Or in the nonlinear case, you can actually say that I have this energy functional. Okay, so you can do it. Okay, so this is a particular architecture I would recommend, and that is actually not really that difficult to make. And this is a semi-supervised learning. So what is this is that what this new architecture did. And I will talk about the convolution in details in the next lecture. So here I just give you the big idea. If I have a graph, I can actually have an unsupervised branch, and then I can have a supervised branch here. Okay, so I train the whole thing together by giving a graph and giving a string, and then I actually try to learn the encode feature vector here, and then the encode feature vector here that representing the graph, the embedded version of the graph, and the string would become the input, and then predict the constitutive response. Okay, does that make sense? And basically here, the convolutional neural network is doing two things. One is doing the node embedding, and then another one is to do the graph pooling to actually come up with one vector to represent the whole graph. I can talk about the details, but what you actually should see is the following. If I change the graph, let's say I actually have these two polycrystal, you should get a different encode feature vector like this encode feature vector, and that encode feature vector added as the input should give you different energy functional. Okay, so why the isomorphism important is here. Okay, if I actually have two graphs that represent the same microstructure, but I just label it in a different name. Okay, I call this A, and A, B, C, D, E, and then I call it 1, 2, 3, 4, 5, or maybe another A, B, C, D, E, but I actually changing the order. I should get exactly the same energy functional. If I do not, then it's not permutation invariance, and then that means that how I label those particles are actually changing the energy functional, so that would be wrong. Okay, so here, one thing that are very important, and I will talk about in detail, is that the permutation invariance are actually very important in all the graph neural network related to mechanics, because in a very rare case, you will actually really name them and create an order set. Okay, usually the set are actually not order. I wonder whether you can think of a case out of order. Or maybe in biomechanics, okay, if something is growing, like a tree that are growing, it may make sense to create an order set. You see what I mean? Because the tree, the morphology of the tree is not usually not suddenly happen simultaneously. In some case, depends on what you predict. You may want to form an order set, but in general, it should be permutation invariance, okay? There are other invariants that we need to talk about, like rotations. Here is still important. And here, I just want to show the example just to apply the idea. Okay, so the whole thing is actually not as complicated as many people think. I actually have this graph, and I just want to, and you can easily form the adjacency matrix by looking at which graph I connect. 1 and 2 are connect, 2 to 3 are connect, 3, 4, and 3, 4, and 3, 5 are connect. You can form an adjacency matrix, and then you can easily compute how much neighbor the node has, and then create the degree, and from that you can get the graph Laplacian, and then you can put the feature as the additional input, and then boom, then you get the encode feature vector. Okay. If I skip up all the detail of how to do the convolutional. So, okay, so you can actually put this into a different graph convolutional layer. This is actually in 2017. There are more advanced encoding technique. And sometimes you add some multi-layer perceptron. In between that, we will talk about the setup in details. You can also look at the 224W to get some general idea. But then the idea is the following. After you do the embedding, you do need to check whether the embedding is successful. But okay, so if the embedding is not successful, meaning that if you have two graphs that are collapsed into the same vector space, then the prediction would not work. Okay, what you want is that if physically the two microstructures are actually different, then the energy functional need to be different. And to get into that, the vector need to be different. Okay, you see what I mean? If they are identical, if they are not injective, okay, then the whole thing won't work. Okay, so if you have two graphs, map it into that are actually not identical. G1 is not equal to G2, but you map it into the same vector, then that prediction is actually degenerated. It won't actually give you all the necessary details. At least you lose some information. Okay, then I want to ask you a question in general. Would it happen? in general, it could happen, okay? So there are things that your graph cannot represent, and then you also need to think about, for example, if you look at the combinational graph, it doesn't distinguish the cycle. I think you also talk about it in the graph neural network. So you do need to check, and then, but what you can deviate it is to put weight, and then to think about how do you actually represent the data in a proper way by maybe adding weight to actually make the two graphs separatable. But the bottom line is the following: if the embedding is successful, you can actually see that the two microstructure that somehow is similar in the graph sense are actually also have a very little or Euclidean norm distance, okay? In the Euclidean state, the norm is actually measuring the distance, not in the other geometry. Combine what you have into the collab number one and add the graph, and boom, you actually have the final project, okay? I think that this is just the first part of the lecture. I think you changed the energy functional before. I don't want to keep talking about the thing that only I'm interested, but what I can say is that no embedding part. So not the part that you want to generalizing the shape descriptor. You can actually seeing that again, if you actually put the gradient, you get a better sections. And I would actually also strongly recommending that you think about the symmetry if you actually deal with some subproblem that have symmetry. In general, there's a art of generating the data, and this is also something very interesting in the sense that what do you want to generate? If you don't have any prior knowledge, what is your intention in terms of generating the data? You were generating the data in equal spacing, right? Okay, but what does equal spacing mean if you don't know the shape? It has no meaning, okay? You actually have the equal spacing on the grid because you assume the whole thing is flat. But if you actually have a geometry like that, the equal order spacings, if you measure the Euclidean distance, you may actually have a point set that is sampling here. If you have a data that actually have an underlying manifold that look like that, the equal spacing meaning that you're actually sampling here. Okay, why is that? Because the distance is for each of the pair is actually equal, but not but in the sense of the manifold, but not in terms of the Euclidean space. Okay, you see what I mean? So that is also something that could be interesting to explore how do you generating the data. I think I'm running out of time, I guess. Right, so I'm going to have to stop here, but I should leave, so I'll leave right now. So I think I'm running out of time, so next lecture I will continue